Today we will continue with aldehydes and ketones. We have done in chemical properties of aldehydes and ketones. First is nucleophilic addition reactions without elimination of small molecules, and then second is nucleophilic addition reactions with elimination of small molecules, and then next is oxidation reactions. Aldehydes and ketones can be oxidized to carboxylic acids. There are different reagents which can oxidize them. The aldehydes are easily oxidized as compared to ketones, and we can use mild reagents to oxidize aldehydes, but for ketones there is a requirement of strong oxidizing agents, as in ketones we require carbon-carbon bond to be enclaved, but in aldehydes there is no carbon-carbon bond breakage. So now let's start with first is in aldehydes. These can be easily oxidized as we already talked about, and thus the reagents can be used are nitric acid, then potassium permanganate, potassium dichromate. In this, when aldehydes are oxidized, they give carboxylic acids. That is, if there is RCHO, we will get RCOOH. And then the aldehyde which has the number of carbons in starting, this carboxylic acid will have the same number of carbon as present in the starting aldehyde. Example, CH3CHO, that is acetaldehyde, or it is IUPAC's name is ethanol. When it is oxidized with any of these reagents, then we get carboxylic acetic acid, that is ethanoic acid. And now the ketones cannot be easily oxidized and require powerful oxidizing agents, that is like concentrated nitric acid, potassium permanganate, potassium dichromate in H2SO4, etc. at elevated temperatures, in which carbon-carbon bond breakage takes place. That is, this bond is breaking and then we get mixture of carboxylic acids, that is with these two carboxylic acids RCOH, and then here again R and carbon, that is RCOH. Same carboxylic acids are formed in this particular general ketone. Now if it is unsymmetrical, so what if suppose this group is different and this group is different, then the carbonyl group will go with which alkyl group? This is based upon one rule, that is Puffeff's rule. In this bond can also breakage of this bond can also take place, and of this also can also take place. So question is, which will break? In this, it is according to Puffeff's rule. According to Puffeff's rule, during oxidation of unsymmetrical ketones, the cleavage occurs in such a way that smaller alkyl group stays with keto group, that is smaller alkyl group will go with carbonyl group. So this bond breakage will take place. And so in this particular example, with concentrated nitric acid we will get acetic acid, and here again acetic acid. Here there are two carbons on the left side and two carbons on the right side, so both are the carboxylic acids with two carbons, that is ethanoic acids. Now these aldehydes and ketones can also be distinguished by the reagents which are used for their oxidation. As we have discussed, in aldehydes weak oxidizing agents can be used for the oxidation. So these Tollens reagent, Fehling solution, Benedict solution, these are the mild reagents, and these can oxidize only aldehydes. That is, these tests can be used for the distinction of aldehydes and ketones. That is, these tests will be given by the aldehydes and not by the ketones. And so what are these tests are? These tests are important, and this can be asked directly or in comparison, where two aldehyde or ketones are given and we have to distinguish them by chemical test. Then also we can use these tests. So first test, what is Tollens reagent test? In Tollens reagent test, it is a ammonical solution of silver nitrate. It is a ammonical solution of silver nitrate, that is AgNO3, and this the aldehyde reduces silver ion to the metallic silver, that is it gives silver mirror, as we can see in this equation. This is the aldehyde, and with ammonical solution of silver nitrate, when we treat, that is this is tolerance reagent. Ammonical solution of silver nitrate gives this complex ion, and that is tolerance reagent. It reacts in alkaline medium with this to give salt of acid, and then water, then silver mirror, plus this is important, and plus it is ammonia. So this silver mirror is important, and this is formed, and this is seen when if we do this in lab, then the sides of test tube shine like a mirror, which indicates the silver mirror test. So it is only given by the aldehydes and not by the ketones, so we can easily distinguish between them by this test. So the second is Fehling solution test. In this test, Fehling solution consists of two solutions, that is Fehling solution A and then Fehling solution B. So what is the Fehling solution A is? It is a aqueous solution of copper sulfate. It is aqueous solution of copper sulfate. And Fehling solution B is a alkaline solution of sodium potassium tartrate, or we can say it is Ruchelli salt. So these two solutions are first mixed in equal amounts, and then we get out of these, that is Cu2 positive ion in the alkaline medium. This reacts with aldehyde to give salt of acid, and this Cu2O cuprous oxide, and it has red PPT, and this indicates that the presence of aldehyde. So aldehydes only give this test, and ketones do not give this test. By this also we can distinguish the aldehydes and ketones. So these are the two main tests, and the third magnetic solution is also similar to the Fehling solution, in which also this Cu2 positive ions react with the aldehydes, and we get the same red PPT of cuprous oxide. So Fehling solution and magnetic solution are they have the same equations. And so next is the haloform reaction. Haloform reaction is equally important. In this, aldehyde or ketones which have methyl ketone groups, that is this group, which have methyl ketone groups, give this test, haloform test, in which the halogen, that is chlorine or iodine, are treated in the presence of dilute NaOH to give haloform, and this has yellow color in case of iodine, and in case of chlorine it has pale yellow color. So this reaction is haloform reaction, in which aldehydes or ketones having at least one methyl group attached to the carbonyl carbon, that is methyl ketones, react with halogen, chlorine, iodine in the presence of dilute NaOH to give haloform with yellow PPT. This reaction is called haloform reaction. So yellow PPT indicates that it is the compound with methyl ketone group, and it is given by a haloform. In this case it is a iodoform. So if it is iodine, then we get iodoform. If it is chlorine, then we get chloroform. So in this, the acetaldehyde is taken. Acetaldehyde has CH3CO group, so it is a methyl ketone, and when it reacts with iodine in the presence of NaOH, it gives this salt of acid and then the iodoform with yellow PPT. So in any compound in which this group is present, methyl ketone gives this reaction. Suppose we take these two examples. This is a 1, 2, 3, 4, 5 carbons. In this again 5 carbons. So what is the difference? It is 2 pentanone and it is 3 pentanone. It is 2 pentanone and it is 3 pentanone. So in this, out of these two compounds, which will give iodoform test? This first will give iodoform test. And it will give yellow PPT with iodine and NaOH. So and second will not give. So if they are present in two different tubes, we can easily identify out of these tubes which is 2-pentanone and which is 3-pentanone, because 2-pentanone will give yellow PPT while the other will not give. So 2-pentanone will give haloform reaction. That is, 2-pentanone and 3-pentanone can be distinguished by this test, and in this, so if it is this will give the iodoform test. So iodoform test can be carried out with iodine and sodium carbonate. Instead of sodium hydroxide, we can also use sodium carbonate, and again this iodoform is formed. If we treat acetone with iodine and sodium carbonate, this iodoform test is given. So it again indicates that this compound has a methyl ketone group. So, and for the 2-pentanone 3-pentanone, the reaction can be written as, this is 2-pentanone with NaOH and iodine gives this yellow PPT, and but this will give no reaction. So whenever you have to give chemical test, you must write equations. If you will not write equations, then the number can be detected. So these are the oxidation reactions. Next we start with reduction reactions. In reductions, the reduction of carbonyl group can take place to alcohols. That is, aldehyde ketones can be reduced to alcohols. In alcohols, first is reduction to alcohols, or second is reduction to hydrocarbons. They can be reduced to alcohols or they can be reduced to hydrocarbons. First is reduction to alcohols. Reduction of aldehydes or ketones can be done to alcohols with different reagents. First is hydrogen in the presence of nickel, palladium or platinum, and this is also called catalytic hydrogenation because addition of hydrogen in the presence of catalyst. So it is catalytic hydrogenation. Second, lithium aluminium hydride can also be used, and it is more reactive than the sodium borohydride. Third, sodium borohydride can also be used, and then fourth, isopropyl alcohol can also be used in the presence of aluminium isopropyl oxide. So we have a different reagents which can be used for the reduction of aldehydes and ketones to alcohols. In all these cases, if we use first then hydrogen, aldehyde ketones are treated with hydrogen in the presence of this catalyst, and we get that is, instead of double bond O, we get HOH, CHOH, that is, alcohol is formed. So if we take a particular example, CH3CHO, if it is treated with hydrogen in the presence of nickel, then this here the C double bond O group is present, and this gets reduced to CHOH, and one hydrogen already present, so it is CH2OH, that is alcohol. So aldehydes give primary alcohols and ketones give secondary alcohol. Ketones give secondary alcohol. This point here is to be noted, that is, aldehydes give primary alcohols and ketones give secondary alcohols. In ketones, suppose it is acetone, if we treat with hydrogen in the presence of nickel, then we get CH2CHOH to this carbon. Here in this carbon, instead of CO, CHOH will be added, that is CHOH, and CH3 is as such. So we get secondary alcohol, and it is propane 2-ol. So it is only it is alcohol. So aldehydes give primary alcohols and ketones give secondary alcohols. And taking one more example, that is C6H5CH2, it is benzaldehyde. When it is reduced, it gives C6H5CH2OH, that is benzyl alcohol. So any conversion can be asked, like convert propane 2-one into propane 2-one into propane 2-ol. In this, There's one main difference between the two reagents, that is lithium aluminium hydride and sodium borohydride. Both are used for reduction, but as we have already done here also, that lithium aluminium one is more reactive, other is more selective. So in this case, lithium aluminium hydride is more reactive and it is less selective. That is, when it is used, it reduces both double bond and the carbonyl group, so we get this alcohol. But the sodium borohydride is more selective and it reduces only one group, that is only the carbonyl group, and double bond remains as such. So it is lithium aluminium hydride is more reactive and it is more selective. This can be seen by this example. So it is important, it can be asked how we can say that lithium aluminium hydride and sodium borohydride, out of these which is more reactive, which is more selective. How can we show that? This we can show with this example in which both double bond and carbonyl group are present. So next is reduction to hydrocarbons, that is C double bond O group is reduced to CH2, and in this we have first Clemson reduction, then Wolff-Kishner reduction, then with hydrogen iodide in the presence of red phosphorus. So first is Clemson reduction. In Clemson reduction is aldehydes or ketones are treated with zinc amalgam in the presence of concentrated HCl, and then these provide nascent hydrogen, and this gives the, that is this CHO group, or we can say C double bond O gives CH2, so it does CH3. So alkane is formed, or aldehyde ketone is reduced to hydrocarbons. In particular example, suppose it is CH3CHO, then with this, that is with nascent hydrogen, it gives CH3CHO. Instead of CO, we will have two hydrogens, one is already present, so CH3, so ethane is formed. Similarly, in this 3 carbons are there, so in this alkane of 3 carbons, that is propane is formed. So Clemson reduction is, it is the reduction of aldehyde or ketones with zinc amalgam and concentrated HCl. So next is Wolff-Kishner reduction. In Wolff-Kishner reduction is aldehyde of ketone is treated with hydrazine, ketone is treated with hydrazine, and then this is formed, and then this resulting intermediate when treated with potassium hydroxide in the presence of glycol, then we get the alkane, that is hydrocarbon. So if taking particular example, that is CH3CHO, that is aldehyde with hydrazine gives first hydrazone, and then with KOH and glycol ethane is formed and nitrogen is released. So similarly as with this acetophenone with hydrazine, then this, in this actually this water is removed and as such NH2 is attached, and that is hydrazone, and then with this gives this. Similarly in this O and this hydrogen, that is as water is removed, and this group is attached to carbon, so carbon double bond NH2, and this with potassium hydroxide and glycol gives this hydrocarbon. So this is the Wolff-Kishner reduction. And next is reduction with HI, hydrogen iodide in the presence of red phosphorus, then again this is reduced to H2, that is RCH3 is formed, and water plus iodine. Similarly, if we take an example, and then again we get a alkane. So these are the 3 main reagents by which aldehydes and ketones can be reduced to hydrocarbon. That is, first is Clemson reduction, then Wolff-Kishner reduction, and third is with HI in the presence of red phosphorus. And then the reduction to alcohols can also be done with one reagent, that is with MPV reduction, that is Meerwein-Ponndorf-Verley reduction. In this, it is used for ketones only. These ketones are treated with isopropyl alcohol in the presence of aluminium isopropoxide, and then we get secondary alcohols. This ketone gives secondary alcohol. So this is our main product, and it's different that this isopropyl alcohol gives the ketone, it gives acetone. So in the main is in Meerwein von Wally reduction, ketones are treated with isopropyl alcohol and aluminium isopropoxide, and secondary alcohols are formed. So then next is this is all about oxidations and reductions, and then comes the miscellaneous reactions. In miscellaneous reactions, we have first as aldol condensation reaction, then cross aldol reaction, then Cannizzaro reaction, and then many more reactions like polymerization and polymerization reactions, and then Tichenko reaction, and all these will continue in the next video. So thank you.